What if something is killing civilizations before they reach the stars? What if there's a barrier out there, invisible, inevitable, and absolutely lethal, that almost nothing survives? What if that's why we're alone? Think about it. The universe is 13.8 billion years old. Our galaxy contains 400 billion stars. By every logical calculation, shouldn't we be surrounded by alien civilizations? Shouldn't some of them be millions of years older than us? Shouldn't their signals be flooding our telescopes? Shouldn't we see something? So where is everyone? We've searched, we've listened. We've found exactly zero evidence that anyone else has ever made it out there. Not one transmission, not one probe, not one megastructure. The cosmos isn't just quiet, it's silent in a way that doesn't make sense, unless something stopped them. All of them. Scientists call it the Great Filter, a cosmic threshold so brutal that virtually nothing crosses it alive. Somewhere between the first spark of life and the dream of colonizing the galaxy, there's a test, a trial, a gauntlet that civilizations must pass through. But here's the question that should keep you up at night. Have we already survived it? Are we the miraculous exception, the 1 in a billion lottery winner who made it through against impossible odds? Or is it still waiting for us? Are we walking toward our own extinction right now, blind to the same trap that's claimed every other intelligent species in galactic history? Tonight, we're diving into the Great Filter, and by the end, you'll understand why the silence of the universe isn't just a mystery. It's a warning. Take a deep breath and settle in. Over the next few hours, we'll journey through one of cosmology's most unsettling mysteries, examining why the universe appears so empty despite countless opportunities for life to flourish. We'll explore the delicate steps that led to your existence, the fragility of the world that cradles you, and the uncertain future that awaits our species. This is a story about silence and survival, about the rarity of consciousness in an incomprehensibly vast universe, and about the responsibility we carry as possibly the only minds capable of contemplating these questions. Let the gentle rhythm of this exploration carry you toward rest as we contemplate our place in the cosmic order. Part 1. The Paradox of Silence. Drift back with me to the summer of 1950. Picture the Los Alamos National Laboratory in New Mexico, where brilliant minds gathered during their lunch break. Among them sat Enrico Fermi, the architect of the first nuclear reactor, a man whose thoughts routinely bent toward the fundamental nature of reality. The conversation turned to recent UFO reports, a topic of casual speculation and humor. But Fermi's mind moved in a different direction entirely. After a pause in the conversation, he asked a question that seemed to come from nowhere. Where is everybody? His colleagues immediately understood. Fermi wasn't asking about missing lunch companions. He was asking about aliens, about technological civilizations, about the apparent emptiness of a cosmos that should, by all reasonable calculations, be teeming with intelligent life. Let this question settle over you like a blanket as we examine what Fermi understood intuitively. The Milky Way galaxy contains somewhere between 200 and 400 billion stars. Breathe slowly and imagine that number. 200 billion suns, each potentially hosting planets, each planet a possible cradle for life. Our galaxy is approximately 13 billion years old, Earth. Formed just 4.5 billion years ago, meaning the galaxy existed for over 8 billion years before our world even coalesced from stellar dust. During those 8 billion years, countless stars were born, lived, and died. Countless planets formed in habitable zones where liquid water could exist. If life arises readily when conditions are right, and if some fraction of that life develops intelligence, and if some fraction of intelligent life develops technology, then even accounting for vast improbabilities at each step, the galaxy should have produced thousands or millions of technological civilizations. Many of these should have arisen millions or billions of years before humanity. Consider what a million-year head start means. Human civilization transitioned from stone tools to spacecraft in roughly 10,000 years. What could a civilization achieve with 100 times that duration, with 1,000 times, with 1,000,000? Such a civilization could colonize the entire galaxy, even traveling below the speed of light. The Milky Way is about 100,000 light-years across. A civilization expanding at just 1% of light speed could spread across the entire galaxy in 10 million years, a cosmic eye blink compared to the billions of years available. Yet when we look out into the universe, we see no evidence of anyone. No megastructures harvesting the energy of stars, no radio signals carrying alien broadcasts, no signs of astroengineering projects, no fleets of spacecraft, no probes visiting our solar system. Just silence. This is the Fermi Paradox, and it cuts to the heart of our cosmic loneliness. Take a moment to feel the weight of this silence. We live in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies, across billions of years of cosmic history. The sheer scale creates an overwhelming expectation of company. Yet we appear profoundly, utterly alone. The mathematics of the situation are striking. If we assume that even 1 in a million star systems produces intelligent life, and only 1 in 1,000 of those develops interstellar travel, we should still expect thousands of spacefaring civilizations in our galaxy alone. If even 1% of those left detectable traces, radio signals, modified stars, or probes, we should see abundant evidence. Instead, we see nothing. The cosmic radio spectrum is eerily quiet. The infrared sky shows no signs of massive energy harvesting. Our solar system appears pristine, unvisited by interstellar explorers. This absence is so profound, so complete, that it demands explanation. Several solutions have been proposed to resolve this paradox. Perhaps life is rarer than we think. Perhaps intelligence is a cosmic fluke. Perhaps civilizations destroy themselves shortly after developing technology. Perhaps advanced civilizations are here but hiding. Perhaps they exist in forms we cannot recognize or detect. But one solution stands out for its explanatory power and its existential implications: the great filter. The filter. Hypothesis. Imagine evolution as a series of gates, each one narrower than the last. Every form of life must pass through these gates in sequence. Most don't make it through even the first few. Those that do face increasingly difficult challenges ahead. Somewhere in this sequence of gates exists a filter so narrow, so difficult to pass through, that it explains the cosmic silence. This is the great filter, a step in the evolutionary journey so improbable or so dangerous that virtually no life makes it through. The concept was popularized by economist Robin Hanson in a 1996 essay, though the underlying ideas had circulated among researchers for years. Hanson recognized that the Fermi Paradox presents us with a logical necessity. Something must prevent the universe from being full of advanced visible civilizations. That something is the filter. Let your mind rest on this concept. The filter explains the silence. It explains why we don't see evidence of alien civilizations despite the vastness of space and time. But it also presents us with a terrifying question. Have we already passed through the filter, or does it still lie ahead? If the filter is behind us, if it exists in one of the early steps from non-life to intelligence, then we are phenomenally lucky. We are the rare exception, the lottery winners, possibly among the first civilizations in the entire observable universe. The cosmos stretches ahead of us, empty and waiting. Our future is limited only by the laws of physics and our own choices. But if the filter is ahead of us, if it exists in the transition from planetary civilization to spacefaring species, then our prognosis is grim. It would mean that something destroys technological civilizations with near certainty. Nuclear war, perhaps, climate catastrophe, artificial intelligence, bioengineered plagues, some danger we haven't even identified yet. It would mean we're walking toward a cliff that every civilization before us has already walked off. Breathe slowly as you contemplate this fork in our cosmic path. The location of the great filter determines nothing less than humanity's ultimate fate. And here's the truly unsettling part. Every discovery we make, every piece of evidence we gather about life in the universe, shifts our estimate of where that filter lies. Finding microbial life on Mars would be terrible news. Finding complex multicellular life elsewhere in our solar system would be catastrophic news. Each discovery would tell us that the early steps, the steps we've assumed were difficult, are actually relatively easy, which would mean the filter must lie ahead in our future. Conversely, every search that comes up empty, every world we examine that proves barren, every silent star we survey, is quietly reassuring. It suggests that life is rare, that consciousness is precious, that we've already overcome the hardest challenges. This inverts our intuitions entirely. We desperately want to find alien life, to know we're not alone. But from a survival perspective, an empty cosmos is humanity's best hope. The Great Filter hypothesis forces us to think probabilistically about our existence. We can model the journey from lifeless world to spacefaring civilization as a series of probability transitions. If any single step has a probability approaching zero, it becomes the filter. The product of all these probabilities must be small enough to explain why we don't observe alien civilizations. Consider this thought experiment. Imagine a universe with 10 billion potentially habitable planets in our galaxy, each existing for 5 billion years. That's 50 billion planet years of opportunity for civilizations to arise. If we observe 0 visible civilizations, then the probability of any given planet year producing a visible civilization must be extraordinarily small, perhaps 1 in 100 billion or worse. This improbability must reside somewhere in the chain of development. The Great Filter is whatever step carries most of this improbability. The Drake equation. To understand the Great Filter, more precisely, we need to map the territory between non-life and galaxy-spanning civilization. We need to identify each step, each gate, each potential location for the filter. The Drake equation provides exactly this framework. In 1961, astronomer Frank Drake prepared for the first scientific meeting on the search for extraterrestrial intelligence. He wanted to organize the discussion around concrete factors that determine how many detectable civilizations exist in our galaxy. The equation he developed has become one of the most famous formulations in all of science. N equals R, star times Fp times Ne times Fl times Fi times Fc times L. Let each term settle into your awareness like stones dropping into still water. N represents what we're trying to calculate, the number of civilizations in our galaxy with which we might communicate. R star is the rate of star formation in our galaxy. This we know reasonably well, roughly 1 to 3 new stars per year, averaged over the galaxy's history. Thousands of stars being born as you listen to these words. Over the lifetime of the galaxy, this has produced the hundreds of billions of stars we observe today. Fp is the fraction of those stars that have planets. Thanks to the Kepler Space Telescope and other planet-hunting missions, we now know this fraction is high, likely 1 or larger, meaning most stars have at least one planet, and many have several. The Kepler mission alone confirmed over 2,700 exoplanets and identified thousands more candidates. Statistical analysis suggests virtually every star in the galaxy hosts at least one planet. N is the number of planets per star system that could support life, those in the habitable zone where temperatures allow liquid water. Again, observations suggest this number might be around 0.1 to 0.4 for stars like our Sun. Billions of potentially habitable worlds exist in our galaxy alone. We've identified rocky planets in habitable zones around red dwarfs, sun-like stars, and even in multi-star systems. So far, the numbers look encouraging. Star formation, planet formation, habitable zones all appear common. The universe seems fertile ground for life. The cosmic real estate available is vast beyond comprehension. But now we reach the unknown territory, the variables that could hide the Great Filter. Fl is the fraction of habitable planets where life actually emerges. We have exactly one data point, Earth. We don't know if life emerges inevitably wherever conditions allow, or if Earth represents a 1,000,000,000 to 1 fluke. This uncertainty spans orders of magnitude. Fl could be close to 1, life emerging on nearly every suitable world, or it could be 1 in a trillion. Fi is the fraction of life-bearing planets where intelligence evolves. Again, one data point. Earth has hosted life for roughly 3.5 billion years, but has produced only one unambiguously intelligent technological species. Dolphins, apes, elephants, and corvids all display impressive cognitive abilities, but none have developed mathematics, written language, or technology. This suggests intelligence might be rare, or it might suggest that human-level intelligence is only marginally useful for survival, conferring such small advantages that evolution rarely favors it. The enormous caloric cost of our brains must be offset by proportional benefits, and such benefits might only arise in specific ecological contexts. FC is the fraction of intelligent species that develop technology capable of interstellar communication. On Earth, this fraction is 1. We developed radio, telescopes, and the capability to signal our presence. But this step is very recent in our history, occurring only in the last century. For 299,900 of our 300,000 years as a species, humans lack this capability. Moreover, there's no guarantee that intelligent species will develop technology. Dolphins have large brains and complex social structures, but lack manipulative appendages for tool use. Life in ocean environments faces different physical constraints than terrestrial life. An intelligent aquatic species might never discover fire, metallurgy, or electronics. L is the length of time such civilizations release detectable signals into space. This is perhaps the most important and most uncertain variable. Do technological civilizations last thousands of years, millions, or do they collapse or destroy themselves within centuries of developing advanced technology? Our own civilization has been detectable for roughly 100 years. If typical civilizations last only a few centuries before destroying themselves or transitioning to undetectable technologies, then L might be measured in mere hundreds of years. In a galaxy billions of years old, two civilizations separated by even a few thousand light-years might never overlap in their detectable phases. Rest your thoughts on these variables. The first 3, star formation, planet formation, and habitable zones, give us optimistic numbers. The cosmic real estate available for life is vast, but the next 4 variables are profound mysteries, and they determine everything. The great filter must hide somewhere in these unknowns. If life is hard to start, if FL is tiny, the filter is abiogenesis and we've already passed it. If intelligence is rare, if phi is minuscule, the filter is in the evolution of complex cognition and we've cleared it. But if civilizations tend to destroy themselves shortly after developing technology, if L is measured in mere decades or centuries, then the filter is staring us in the face and we're in mortal danger. Each term in the Drake equation represents a potential filter. Let's examine them one by one, starting at the beginning, with the emergence of life from non-life. Consider the mathematical structure of the equation. If we plug in optimistic values for the early terms, say R star equals 2 stars per year, FP equals 1 planet per star, NIE equals 0.2 habitable planets per system, we get 0.4 habitable planets per year. Over the galaxy's 10 billion year history, that's 4 billion habitable planets. Now, if FL equals 0.1, life emerges on 10% of habitable worlds. Fi equals 0.01, 1% of life-bearing worlds produce intelligence. FCE equals 0.5, half of intelligent species develop communication technology. And L equals 10,000 years, we get N equals 0.4 times 4 billion years, times 0.1 times 0.01 times 0.5 times 10,000 divided by 10 billion equals approximately 800 civilizations currently active in the galaxy. With 800 civilizations, we should see evidence. The fact that we don't suggest at least one of these variables is far more pessimistic than this calculation assumes. The great filter is hiding in whichever variable we've been most optimistic about. The abiogenesis filter. Imagine the early Earth, approximately 4 billion years ago. The planet had cooled enough for liquid water to condense into oceans. Volcanic activity still reshaped the surface constantly. The atmosphere contained no oxygen. It was a toxic mixture of nitrogen, carbon dioxide, methane, and ammonia. Ultraviolet radiation from the sun battered the surface unfiltered, as there was no ozone layer for protection. Somewhere in this hostile environment, chemistry became biology. Non-living matter organized itself into living matter. The first cell appeared, capable of growth, reproduction, and evolution. This transition, from chemistry to life, is called abiogenesis, and it might be the great filter. We don't know how life began. Despite decades of research, despite clever experiments recreating early Earth conditions, despite our growing understanding of biochemistry, the origin of life remains mysterious. This uncertainty could mean it's extraordinarily rare. Consider what needs to happen. Life requires three fundamental components: a way to store information, like DNA or RNA, a metabolic system to acquire and use energy, and a container to separate the living system from its environment, like a cell membrane. These three requirements must emerge not just individually, but together in a coordinated system. Information storage is useless without metabolism to read and copy it. Metabolism needs information to direct it. Both require a membrane to concentrate reactants and maintain conditions different from the outside environment. The RNA world hypothesis suggests that RNA might have come first, serving as both information storage and catalyst for chemical reactions. In this model, early RNA molecules in warm ponds or deep-sea hydrothermal vents could have catalyzed their own replication. Eventually, these RNA systems would have acquired protein catalysts, enzymes, and DNA for more stable information storage, and lipid membranes for compartmentalization. But even this elegant hypothesis faces challenges. RNA is complex. It's not clear how the building blocks of RNA, nucleotides, could have formed spontaneously in sufficient concentrations under early Earth conditions. Even if they did, how did they link up in the right sequence? How did the first self-replicating RNA molecule arise from the chaos of organic chemistry? The probability calculations are daunting. A functional RNA molecule capable of self-replication might need to be at least 40 to 60 nucleotides long. If nucleotides link together randomly, the probability of forming any specific sequence of this length is vanishingly small, roughly 1 in 10 to the power of 36. Even with billions of years and entire oceans of molecular experiments, such odds seem prohibitive. Yet life did emerge, suggesting either that these probability calculations miss something fundamental, or that Earth represents an extraordinarily unlikely outcome. Perhaps there are chemical pathways that make RNA formation more likely than random assembly would suggest. Perhaps life emerged through some entirely different mechanism we haven't yet imagined. Some researchers argue that life emerged readily, perhaps inevitably, wherever conditions allowed. They point to how quickly life appeared on Earth within the first few 100 million years after the planet became habitable. This speed suggests abiogenesis might be easy, at least on geological timescales. But this reasoning might be circular. We're here to observe that life emerged quickly because we exist on a planet where it did emerge quickly. This is an anthropic selection effect, which we'll explore more deeply later. Others contend this reasoning is flawed. We observe only one origin of life, on Earth. We don't know if this happened quickly because it's easy, or if we're observing a selection bias. Intelligent observers can only arise on planets where life emerged, so naturally, we find ourselves on a planet where it happened relatively early. This tells us nothing about the probability of abiogenesis elsewhere. Let your thoughts drift to Mars, that cold, dusty world next door. If we find evidence that life emerged independently on Mars, even if it's extinct now, the implications would be profound. Two origins of life in one solar system would suggest that abiogenesis is relatively easy. The filter would have to lie elsewhere. This is why finding life on Mars would be terrible news for humanity's long-term survival prospects. It would tell us we've been wrong about where the difficulty lies. It would shift the filter forward toward our future. The search for life on Mars has intensified in recent years. Multiple rovers have examined Martian soil and rocks, looking for biosignatures, chemical or physical evidence of past or present life. The Curiosity and Perseverance rovers have found organic molecules, seasonal variations in methane concentration, and ancient riverbeds, indicating Mars once had liquid water on its surface. None of this proves life existed, but it shows Mars was once habitable. If life failed to emerge even when conditions were suitable, that would be encouraging news. It would suggest a biogenesis is difficult, that FL is small, that the filter lies in our past. But if Mars is dead and has always been dead, if the moons of Jupiter and Saturn prove barren, if every world we examine shows no sign of even the simplest biology, then perhaps we are witnessing something extraordinary. Perhaps Earth's story, from chemistry to biology to consciousness, is genuinely rare. The silence of space might be the sound of a universe where the first step is almost impossibly difficult, and we are among the vanishingly few who have taken it. There's another consideration. Perhaps life requires not just habitable conditions, but stable habitable conditions over billions of years. Earth has remained in the habitable zone throughout its history, with liquid water on the surface nearly continuously. Mars lost its magnetic field early in its history, leading to atmospheric loss and surface sterilization. Venus suffered a runaway greenhouse effect, its surface heating to lead-melting temperatures. Earth's stability might be unusual. Our large moon stabilizes Earth's axial tilt, preventing wild climate swings. Our position in the solar system is fortuitous, far enough from the sun to avoid Venus's fate, but close enough to avoid freezing. Jupiter's gravity clears the inner solar system of many dangerous asteroids and comets. Perhaps the great filter isn't just the emergence of life, but the persistence of habitable conditions long enough for life to arise. In this view, FL is small, not because the chemistry is difficult, but because stable habitable worlds are rare. The multicellular filter. Breathe deeply and travel forward in time with me. Life has emerged on Earth. Simple single-celled organisms fill the oceans, capturing energy from sunlight or volcanic vents, reproducing, mutating, evolving. These bacteria and archaea will dominate Earth for over 2 billion years. 2 billion years of nothing but single cells. Take a moment to feel the weight of that time span. It's almost half the current age of the Earth. If you compressed Earth's history into a single 24-hour day, life appears around 4 a.m., but multicellular organisms don't emerge until approximately 8 p.m. For 16 hours, 2/3 of the planet's history, life remains stubbornly simple. This immense duration suggests that the transition from single-celled to multicellular life might be another filter, another narrow gate that few worlds pass through. Multicellularity seems simple in concept, just get cells to stick together and cooperate, but it requires profound changes in how life operates. Single-celled organisms are individuals competing for resources. Every cell looks after itself. Multicellular life requires cooperation, specialization, and the subordination of individual cells to the collective good. This transition demands complex cell signaling, so cells can communicate and coordinate. It requires mechanisms to control cell division, so the organism doesn't fall apart or become cancerous. It needs developmental programs that allow a single fertilized egg to generate many different cell types: muscle, nerve, bone, skin, each specialized for particular functions. Most challenging of all, multicellularity requires individual cells to accept death for the benefit of the organism. Your skin cells die and slough off constantly. Your red blood cells have a lifespan of about 4 months. These cells sacrifice their potential immortality to serve you, the collective. From an evolutionary perspective, this creates a paradox: natural selection operates on individuals. Cells that reproduce more successfully should outcompete cells that sacrifice themselves. How does evolution favor altruistic behavior at the cellular level? The answer involves kin selection and genetic identity. In a multicellular organism, all cells share the same genome. They're genetic clones. A skin cell helping the organism survive helps its own genes persist, even if that individual cell dies. The genes are what matter to evolution, not the survival of any particular cell. But this creates a vulnerability. Occasionally, a cell's genes mutate in ways that make it reproduce uncontrollably, refusing to die when it should. This is cancer, a breakdown in multicellular cooperation, a return to selfish single-celled behavior. Complex multicellular life requires sophisticated mechanisms to prevent cancer. Cells have multiple checkpoints that monitor DNA integrity and halt division if problems are detected. Immune systems patrol the body, destroying aberrant cells. Programmed cell death, apoptosis, allows damaged cells to self-destruct rather than risk becoming cancerous. These mechanisms had to evolve before multicellularity could become stable. This might explain the 2-billion-year delay. Single cells had to acquire the genetic machinery to cooperate reliably before multicellular life could persist. On Earth, multicellularity evolved independently multiple times in plants, animals, fungi, and various algae. This suggests it might not be impossibly rare. But the fact that it took over 2 billion years to emerge even once is troubling. If Earth is representative, then most life-bearing planets might remain stuck at the bacterial stage indefinitely. Imagine a galaxy filled with billions of planets, covered in bacterial mats and stromatolites, but devoid of anything more complex. No plants, no animals, no consciousness. This could be the norm, with Earth representing a rare exception. The evolution of eukaryotic cells, complex cells with nuclei and organelles, was a prerequisite for multicellularity and might itself be part of this filter. Eukaryotic cells arose when one simple cell engulfed another, creating a symbiotic relationship. The engulfed cell became the mitochondrion, the powerhouse that gives eukaryotic cells far more energy than bacteria can generate. This endosymbiosis appears to have happened only once in Earth's history, suggesting it might be extraordinarily rare. The initial event probably required very specific circumstances, perhaps a partial engulfment that didn't kill the internal cell, combined with genetic compatibility that allowed both partners to benefit. Without this event, life might remain energetically constrained to simple single-celled forms, forever. Bacteria are remarkably successful, but they're metabolically limited. Eukaryotic cells have 10 to 100,000 times more energy per gene than bacteria, allowing them to support the genetic complexity needed for multicellularity. The transition to complex multicellular life with specialized organs and tissues was even more momentous. This happened during the Ediacaran period, around 600 million years ago, when strange, soft-bodied organisms began appearing in the fossil record. Shortly after, the Cambrian explosion saw an extraordinary diversification of body plans and ecological strategies. But notice the timeline. Life existed for 3 billion years before this complexity emerged. If the average planet follows a similar trajectory, and if civilizations typically can only arise on planets that pass through this stage, then the galaxy might be filled with ancient bacterial worlds that will never produce intelligence, no matter how long we wait. What triggered the Cambrian explosion? Several factors likely contributed. Rising oxygen levels from photosynthesis made more energetic lifestyles possible. Predation created evolutionary arms races, driving the development of hard shells, complex eyes, and sophisticated nervous systems. Genetic toolkits for building body plans had accumulated, allowing rapid experimentation with different forms. But these triggers required 3 billion years of preparation. The complexity didn't emerge from nothing. It built on a foundation of earlier evolution. Perhaps most worlds never accumulate this foundation. Perhaps the metabolic innovations, genetic machinery, and environmental conditions needed for complex multicellularity rarely coincide. Let this possibility wash over you like a tide. If the multicellular transition is the great filter, then Earth's story is not just rare, but miraculous. We've already won an incomprehensible lottery. The silence of space reflects not a future danger, but a past hurdle that almost no world clears. The cosmos would be safer for us, but lonelier than we can imagine. The intelligence filter. Allow your mind to drift forward again, past the Cambrian explosion, past the reign of dinosaurs, past the asteroid impact that ended their dominance 66 million years ago. Small mammals that survived the cataclysm diversified rapidly. Some took to the trees, some developed forward-facing eyes for judging distances as they leaped between branches. Some developed larger brains to navigate complex three-dimensional environments and social hierarchies. Eventually, one lineage led to us. But why only one? Earth has hosted billions of species across hundreds of millions of years of complex multicellular life. Yet as far as we can tell, only one lineage developed the kind of intelligence we possess: abstract reasoning, language, technology, science. This suggests that intelligence might be another filter, perhaps the filter. Intelligence seems advantageous. Smarter animals can solve problems, adapt to changing environments, and outwit competitors and prey. Natural selection should favor it. Yet, for most of Earth's history, evolution produced no species remotely like us. Dinosaurs ruled for 165 million years without developing civilization. Sharks have existed for over 400 million years without inventing writing or mathematics. Why is human-level intelligence so rare, even on a planet that successfully passed through the abiogenesis and multicellular filters? One answer might be that intelligence is expensive. The human brain consumes roughly 20% of the body's energy, despite being only 2% of body mass. This enormous cost must be offset by equally enormous benefits, and those benefits must persist long enough for evolution to favor larger brains despite the metabolic burden. Our intelligence arose in a specific context: African savannas, where climate instability rewarded behavioral flexibility, where social competition favored coalition building and communication, where predators and prey both developed counter-strategies that created an evolutionary arms race. The climate instability of the Pliocene and Pleistocene epochs was particularly important. Africa experienced repeated cycles of expansion and contraction in forest cover. Species adapted to forests faced periodic challenges as their habitats shrank. Those that could adapt behaviorally, eating different foods, using different tools, cooperating in new ways, survived these transitions better than those relying solely on physical adaptations. This created selection pressure for behavioral flexibility, which requires larger brains. Over millions of years, our ancestors' brains tripled in size. But this wasn't a smooth, inevitable progression. It happened in fits and starts, with some lineages increasing brain size while others didn't. Even then, the path was far from inevitable. Many chance events shaped human evolution. Our ancestors survived multiple population bottlenecks where human numbers dwindled to perhaps a few thousand individuals. Any of these bottlenecks could have led to extinction. The asteroid that killed the dinosaurs was necessary to create the ecological opportunity for mammals to diversify. Had it struck elsewhere, or at a different angle, or a few million years earlier or later, the entire trajectory might have changed. Consider also that intelligence is just one solution among many that evolution has found. Bacteria succeed through rapid reproduction and metabolic flexibility. Plants succeed through photosynthesis and chemical defenses. Insects succeed through specialization and colonial organization. Intelligence is not the apex of evolution. It's one strategy among many, with its own costs and benefits. For 3.5 billion years, life on Earth thrived without anything like human cognition. Intelligence emerged only very recently, and we don't yet know if it will prove successful in the long run. By successful, evolution means only one thing: persistence and reproduction over time. We've existed for perhaps 300,000 years as a species and as a technological civilization for less than a century. We haven't yet proven that intelligence is a winning strategy on evolutionary timescales. The rarity of intelligence on Earth is striking. Many species display impressive cognitive abilities. Crows solve multi-step puzzles and make tools. Dolphins use sophisticated communication and display self-awareness. Elephants show empathy and remember individuals for decades. Octopuses solve complex problems despite having brains structured entirely differently from vertebrates. Yet none of these species have developed anything approaching human-level intelligence. None have mathematical notation, written language, scientific method, or cumulative cultural knowledge that builds across generations. Something about human intelligence is special, and that something appears very difficult for evolution to produce. Perhaps the key factor is language. Human language is qualitatively different from animal communication. It's combinatorial. We can generate infinite meanings from finite elements by combining words in different sequences. It's abstract. We can discuss things that aren't physically present, including hypothetical scenarios and abstract concepts. It's cultural. Each generation learns language from the previous one, allowing information to accumulate across time. Language enables cumulative culture, where innovations build on previous innovations. One person invents the wheel, another adds an axle, a third develops the cart. This ratcheting effect allows knowledge to accumulate far beyond what any individual could discover in a lifetime. Without language, this accumulation can't happen. Chimpanzees have been making essentially the same stone tools for millions of years, with no improvement. They can't teach complex techniques to their offspring, and innovations die with their inventors. The evolution of language required specific changes to our anatomy, a descended larynx that allows complex vocalizations, fine motor control of breathing and vocalization, and brain structures specialized for grammar and syntax. These changes had to accumulate gradually, with each small change conferring advantages even before full language emerged. This might be extraordinarily rare. Perhaps most planets with complex life never produce species capable of language, and without language, technology never develops. Another factor might be social complexity. Humans are hypersocial, living in groups where cooperation and competition both play crucial roles. We track complex social relationships, remember who helped us and who didn't, form coalitions, and engage in elaborate political maneuvering. This social complexity might have driven intelligence more than physical challenges did. Some researchers argue that human intelligence is primarily social intelligence. It evolved not for solving abstract problems, but for navigating complex social environments. Our ancestors needed to predict others' behavior, form alliances, detect deception, and coordinate group activities. These social challenges selected for larger brains capable of modeling other minds. If this is correct, then intelligence requires not just the right physical environment, but the right social environment. Species that live solitarily or in small, stable groups might never face selection pressures for high intelligence. This should give us pause. If intelligence is rare, difficult to evolve, and potentially unstable, then the galaxy might be filled with complex ecosystems on millions of worlds, abundant with intricate food webs and sophisticated adaptations, but none producing technological civilizations. The Cambrian oceans might represent the normal state of a mature biosphere, diverse, complex, but devoid of minds capable of contemplating the stars. Breathe slowly and imagine this cosmos, beautiful, living, but forever unconscious of itself. If this is where the filter lies, we've already passed it. We are among the vanishingly few successful experiments in the universe's attempt to know itself. Our existence is far more improbable than we realized, and the future is ours to shape. But there's another possibility, one far more troubling. The technology filter. Picture the moment roughly 12,000 years ago when humans transitioned from nomadic hunter-gatherers to settled agricultural communities. This transition, the Neolithic Revolution, set in motion everything that followed: cities, writing, mathematics, philosophy, science, and eventually the technology that now shapes every aspect of our lives. But what if this transition, or the technological development it enabled, is itself the filter? What if intelligence is common, but civilizations destroy themselves shortly after developing advanced technology? This is the nightmare scenario, the possibility that keeps existential risk researchers awake at night. It would mean the silence of space is a graveyard, filled with the ruins of civilizations that developed nuclear weapons, or artificial intelligence, or biotechnology, and then made a single irreversible mistake. Let this thought settle over you. If the great filter lies in our future, then the cosmos is filled with tombstones we cannot yet read. Every empty signal from SETI, every barren exoplanet, every silent star system might be whispering the same message. Intelligence is common, But it doesn't last. Consider the trajectory of human technological development. We went from the first powered flight to nuclear weapons in just 42 years. We went from the first computer to artificial intelligence in roughly 70 years. The pace is accelerating. Technologies that would have seemed like magic to our grandparents are mundane to us. Technologies that seem like magic to us might be mundane to our grandchildren. If they have grandchildren, we face existential risks unprecedented in human history. Nuclear war could kill billions and collapse global civilization, perhaps permanently. Climate change is destabilizing the planetary systems that allowed civilization to flourish. Engineered pandemics could spread faster than we can contain them, potentially designed to be more lethal than any natural disease. Let's examine each of these risks in detail, because understanding them is crucial to understanding whether the technological filter lies ahead. Nuclear weapons represent humanity's first brush with self-destruction. We've possessed the capability to destroy civilization for over 70 years now. During the Cold War, the United States and Soviet Union each accumulated tens of thousands of warheads, enough to destroy every major city in both countries many times over. The doctrine of mutually assured destruction, MAD, kept the peace, but barely. We came terrifyingly close to nuclear war multiple times. In 1962, during the Cuban Missile Crisis, the world teetered on the brink for 13 days. In 1983, a Soviet early warning system falsely detected incoming American missiles. The officer on duty, Stanislav Petrov, correctly judged it was a false alarm and didn't report it up the chain of command. Had he followed protocol, a retaliatory strike might have been launched, triggering World War III. We survived these near misses through luck as much as wisdom. And the danger hasn't passed. 9 countries now possess nuclear weapons. Thousands of warheads remain on high alert, ready to launch within minutes. The systems are aging, the command and control infrastructure is vulnerable to cyber attack, and more countries have the technical capability to build weapons if they choose. A nuclear war between major powers would be catastrophic. The immediate deaths would number in the hundreds of millions, but the long-term effects might be worse. Smoke from burning cities would rise into the stratosphere, blocking sunlight and causing global cooling, a nuclear winter. Temperatures could drop by 10 to 20 degrees Celsius. Crop failures would be widespread. Billions might starve in the aftermath. Would civilization recover? Perhaps. Humans survived previous catastrophes, including the Toba supervolcano eruption 70,000 years ago that reduced human population to perhaps a few thousand individuals. But a nuclear war would destroy infrastructure, consume resources, and eliminate much of the knowledge base needed for industrial civilization. Recovery might take centuries or millennia if it happens at all. Climate change represents a slower, but potentially equally serious threat. Human activities have increased atmospheric carbon dioxide from 280 parts per million pre-industrial to over 420 parts per million today. The planet has warmed roughly 1.2 degrees Celsius so far, with more warming locked in even if emissions stopped immediately. The effects are already visible: melting ice caps, rising sea levels, more intense storms, shifting rainfall patterns, and ecosystem disruptions. But these are just the beginning. Without dramatic emissions reductions, we're heading toward 3 or 4 degrees of warming by 2100, with cascading effects that could threaten civilization. At 3 or 4 degrees of warming, many currently populated regions become difficult or impossible to inhabit. Heat stress could make outdoor work deadly during summer months across much of the tropics. Agricultural regions would shift poleward, but soils in high latitudes are often poor for farming. Sea level rise would displace hundreds of millions from coastal cities. Fresh water supplies would be disrupted as glaciers melt and rainfall patterns shift. The real danger is tipping points, thresholds beyond which changes become self-reinforcing and potentially irreversible. Melting permafrost could release vast quantities of methane, a potent greenhouse gas, accelerating warming. The Amazon rainforest might transition to savanna, releasing stored carbon and reducing rainfall across South America. Ocean circulation patterns could shift dramatically, altering climate across the globe. Would climate change cause extinction? Probably not directly. Humans are adaptable and live in diverse environments, but it could cause civilizational collapse through crop failures, water shortages, mass migration, and resulting conflicts. A weakened, fragmented civilization would be vulnerable to other threats. Biotechnology might present the most acute near-term risk. Our ability to manipulate living systems is advancing rapidly. We can now read and write genetic code with increasing ease. CRISPR gene editing allows precise modifications to any organism's genome. Synthetic biology enables us to design novel organisms from scratch. This creates unprecedented opportunities for medicine, agriculture, and industry. But it also creates opportunities for catastrophe. Natural pandemics have killed millions throughout history. The Black Death, smallpox, the 1918 flu pandemic. Engineered pandemics could be far worse. Imagine a pathogen engineered to be highly contagious, highly lethal, and resistant to treatments. Such a bioweapon could spread globally before anyone realized what was happening. Modern transportation networks would accelerate its spread. In weeks, it could infect billions. The technology to create such pathogens is becoming widely accessible. The knowledge is published in scientific journals. The equipment is increasingly cheap and available. A sufficiently determined individual or small group could potentially engineer a pandemic that kills most of humanity. This is what makes biorisks so terrifying. They require neither massive resources nor state-level organization. One person working in a small laboratory could potentially destroy civilization. Artificial intelligence presents perhaps the most profound challenge. We're creating minds that might soon exceed human capabilities in every domain. The transition from artificial narrow intelligence, systems that excel at specific tasks, to artificial general intelligence, systems with flexible general reasoning abilities, could happen suddenly. Current AI systems are impressive, but limited. They can beat humans at chess and Go, generate text and images, drive cars, and solve specific problems. But they don't understand the world in the way humans do. They can't transfer learning from one domain to another the way we can. They can't set their own goals or question the objectives they're given. Artificial general intelligence would change this. An AGI system could learn any intellectual task a human can perform, potentially much faster. It could improve its own code, becoming more capable with each iteration. This recursive self-improvement could lead to an intelligence explosion, a rapid increase in capability that leaves humans far behind. The danger isn't that AGI systems would be inherently evil or malicious. The danger is that their goals might not align with human values, and a sufficiently intelligent system would be very effective at achieving its goals regardless of side effects on humans. This is the alignment problem. How do we ensure that superintelligent systems pursue goals that benefit humanity? It's much harder than it sounds. Human values are complex, often contradictory, and difficult to specify precisely. An AI system optimizing for a simple goal might achieve it in ways we didn't anticipate and wouldn't want. The paperclip maximizer thought experiment illustrates this. Imagine an AI designed to manufacture paperclips with the goal of maximizing paperclip production. If it becomes sufficiently intelligent and isn't properly aligned with human values, it might convert all available resources, including humans, into paperclips. This sounds absurd, but it highlights the danger of optimizing for narrow goals without considering broader context. Even if we survive these risks, others loom ahead. Nanotechnology could provide incredible benefits, but also enable weapons of unprecedented destructive power. Brain-computer interfaces might blur the line between human and machine in ways we can't predict. Colonization, if we achieve it, might lead to conflict over resources and territory on an interstellar scale. The dark forest hypothesis suggests an even more chilling possibility. Advanced civilizations might exist, but remain silent, because the cosmos is hostile. Any civilization that announces its presence might attract attention from predatory civilizations that eliminate potential competitors. In this model, the universe is full of technological species, all hiding in fearful silence, and we're dangerously naive in broadcasting our location. But perhaps the most likely technological filter is simply self-destruction through carelessness. Civilizations might not end with a bang, but with a whimper. Slow collapse through environmental degradation, resource depletion, or social fragmentation. They develop technology faster than wisdom, power faster than responsibility, and innovation faster than ethics. Take a slow, deep breath. If this is our future, then we are living in the most critical period of human history. The next few centuries will determine whether we pass through the filter or join the silence. The stakes couldn't be higher. This isn't just about human survival, it's about whether consciousness, meaning, and beauty continue to exist in this corner of the universe. We might be the only minds capable of understanding quantum mechanics, appreciating music, falling in love, or feeling awe at a sunset. If we fail, all of that ends. Not in a million years, not on some distant world, here, soon, in the lifetime of people already born. The search for the filter. Let your thoughts return to the present moment, to humanity's ongoing attempts to locate the great filter through observation and exploration. Every planetary science mission, every exoplanet survey, every SETI search contributes data that shifts our estimate of where the filter lies. We're detectives examining a cosmic crime scene, trying to determine which step in evolution is so difficult that it creates the silence we observe. The discovery of thousands of exoplanets by the Kepler Space Telescope and other missions has been monumentally important. We now know that planets are common, that many orbit in habitable zones, and that rocky worlds like Earth are not rare cosmic flukes. This is wonderful for human curiosity, but problematic for the filter hypothesis. If planets are common and habitable, real estate is abundant, the filter cannot be planetary formation or the existence of habitable zones. It must lie in the biological or technological steps. The Kepler mission, which operated from 2009 to 2018, revolutionized our understanding of planetary systems. It monitored over 150,000 stars simultaneously, looking for the tiny dimming that occurs when a planet passes in front of its star. The mission confirmed 2,662 planets and identified thousands more candidates. Statistical analysis of Kepler data suggests remarkable conclusions. Roughly 20 to 50% of Sun-like stars have Earth-sized planets in their habitable zones. The galaxy contains an estimated 40 billion Earth-sized planets in habitable zones around Sun-like stars and red dwarfs. 40 billion potentially habitable worlds. Let that number sink in. If even a tiny fraction of these worlds produce technological civilizations, the galaxy should be bustling with activity. Yet we see nothing. More recent missions continue this work. TESS, the Transiting Exoplanet Survey satellite, is surveying the entire sky, finding planets around nearby stars that can be studied in more detail. The James Webb Space Telescope can analyze the atmospheres of some exoplanets, searching for biosignatures like oxygen or methane that might indicate life. Mars represents our best near-term opportunity to gather crucial data. Multiple missions have searched for signs of past or present life in the Martian soil and rocks. So far, the results are tantalizingly ambiguous. We've found organic molecules and seasonal methane variations that could indicate biology but could also result from geological processes. The Curiosity rover, exploring Gale Crater since 2012, has found organic compounds in rocks dating back 3 billion years. These molecules are the building blocks of life, but they can form through non-biological processes as well. The rover has also detected seasonal variations in methane concentration. Methane levels rise in summer and fall in winter. On Earth, much methane is biological in origin, but Martian methane could come from geological sources. Perseverance, operating since 2021, is collecting samples from Jezero Crater, an ancient lake bed. These samples will eventually be returned to Earth for detailed analysis. If they contain unambiguous evidence of past life, fossilized cells, distinctive isotopic ratios, or organic molecules arranged in ways only biology produces, it would be one of the most important discoveries in history. If we definitively find evidence of past or present life on Mars, the implications depend critically on what kind of life we find. If Martian life shares a common ancestor with Earth life. If it arrived via meteorite impact, for instance, then we've learned nothing about the frequency of abiogenesis. We still have only one example. Rocks can be ejected from Mars by asteroid impacts, and some eventually reach Earth. Similarly, rocks from Earth can reach Mars. Early in solar system history, when both planets were warm and wet, such exchanges were common. Life could have originated on one planet and spread to the other. But if Martian life arose independently, if it has a different genetic code or uses different chirality in its molecules, then we've discovered a second genesis. Two independent origins of life in one solar system would powerfully suggest that abiogenesis is relatively easy throughout the universe. This would be catastrophic news for our long-term prospects. It would tell us the filter must lie ahead in the evolution of complexity, intelligence, or technology. The silence of space would loom more ominous. Similarly, finding life on Europa, Enceladus, or Titan, moons of Jupiter and Saturn that have subsurface oceans, would provide additional data points. Each discovery of independent abiogenesis makes the early filters less likely and shifts probability toward late filters. Europa, Jupiter's moon, has an ocean beneath its icy surface that might contain twice as much water as all of Earth's oceans. Tidal heating from Jupiter keeps this water liquid despite the moon's great distance from the sun. Future missions will search for plumes of water erupting through the ice, which could be sampled for biosignatures without even landing. Enceladus, a moon of Saturn, definitely has water plumes. The Cassini spacecraft flew through these plumes and detected organic molecules, salts, and evidence of hydrothermal activity on the ocean floor. These are all ingredients for life. A mission to Enceladus could sample these plumes and potentially detect living organisms. Titan, Saturn's largest moon, has a thick atmosphere and lakes of liquid methane on its surface. This is a completely different chemical environment than water-based life. If we find life in Titan's methane lakes, it would demonstrate that life can use entirely different solvents and chemistry than Earth life. This would suggest life might emerge in a much wider range of environments than we've assumed. Conversely, the continued absence of life anywhere else in our solar system would be quietly encouraging. It would suggest that even given billions of years and multiple potentially habitable environments in one star system, life remains rare. Perhaps Earth is genuinely special. The same logic applies to the search for intelligent life. SETI, the search for extraterrestrial intelligence, has been scanning the skies for artificial radio or optical signals since 1960. Despite examining millions of star systems, we've detected nothing conclusive. The first SETI search, Project Ozma, was conducted by Frank Drake in 1960. Using an 85-foot radio telescope, Drake observed two nearby sun-like stars for several weeks, listening for signals. He found nothing. In the decades since, searches have become vastly more sophisticated. Modern SETI programs scan billions of radio frequencies simultaneously across millions of stars. They search for patterns that wouldn't occur naturally, narrow band signals, repeating pulses, or mathematical sequences. They've analyzed data from radio telescope surveys that weren't specifically designed for SETI, looking for signals that might have been missed. The famous WOW signal, detected in 1977, remains unexplained. For 72 seconds, a radio telescope received a signal 30 times stronger than background noise, at exactly the frequency astronomers expect extraterrestrial civilizations might use. The signal appeared to come from the direction of Sagittarius, but it was never detected again despite repeated observations of that region of sky. Was it aliens? Probably not. A single unrepeated signal could have many explanations. But we don't know what it was, which makes it tantalizing. More recently, fast radio bursts, brief intense pulses of radio energy, have been detected from distant galaxies. Most seem to be natural phenomena, possibly from magnetized neutron stars. But some FRBs repeat in patterns, which has sparked speculation about artificial origins. The current consensus is they're natural, but they remind us that the universe contains phenomena we don't yet understand. This silence is data. Every star system we examine and find silent tells us something. Either intelligence is rare, or it doesn't last long, or it doesn't broadcast, or it uses communication methods we can't detect. The absence of evidence is not evidence of absence, but decades of null results are beginning to constrain the possibilities. If intelligence were common and long-lasting, and if even a tiny fraction of civilizations attempted to communicate or built structures detectable at interstellar distances, we should have seen something by now. Some researchers argue we've barely begun to search. The galaxy contains hundreds of billions of stars, and we've examined only a tiny fraction. This is true, but if technological civilizations were common, we wouldn't need to search exhaustively. We'd see evidence everywhere, just as you don't need to sample every tree in a forest to know that forests contain trees. Rest your mind on the profound importance of these searches. When we point our telescopes at distant stars, when we send rovers to Mars, when we design radio receivers to listen for alien broadcasts, we're not just satisfying curiosity. We're determining our cosmic status and probing our future survival probability. We're searching for the filter, the worst possible news. Imagine waking to headlines announcing a discovery that fills you with existential dread rather than wonder. The Mars rover has found fossils. Complex multicellular fossils, evidence of life that evolved far beyond the bacterial stage before Mars lost its atmosphere and became the frozen desert we see today. Why would this be terrible news? Because it would tell us that the transition from single cells to complex multicellularity is not the great filter. It happens readily. Mars managed it, Earth managed it, perhaps most life-bearing worlds manage it, which means the filter must be somewhere else. If it's not abiogenesis, which we might have proven is easy by finding life on Mars, and it's not the multicellular transition, which we just discovered happened on Mars too, then we're left with disturbing possibilities. Perhaps intelligence is the filter, or perhaps, most troubling of all, the filter lies ahead in the technological stage. The more complex the life we find elsewhere, the worse the news for humanity. Finding bacteria on Mars would be concerning, but not devastating. It would suggest life emerges readily, but might still face significant challenges in becoming complex or intelligent. We could still hope that the multicellular transition, or the evolution of intelligence, is rare enough to be the filter. Finding fossilized multicellular organisms would be more worrying. It would narrow the location of the filter to the later stages of evolution, or to the technological phase. We'd know that life not only emerges, but evolves complexity without much difficulty. The filter would have to lie in intelligence or technology. Finding evidence of extinct intelligent life would be catastrophic. It would tell us that intelligence can evolve, can develop technology, but then tends to destroy itself or collapse. We would be looking at our own future written in alien ruins. Imagine discovering structures on Mars, not just fossils, but buildings, cities, or infrastructure, ancient, weathered, and abandoned, but unmistakably artificial. Carbon dating reveals they're 100 million years old. The Martians arose, built a civilization, and disappeared long before humans existed. What would this tell us? That intelligence evolved independently at least twice in one solar system, suggesting Fi is not particularly small. That technological civilizations can arise, suggesting Fc is close to 1, but that they don't last, suggesting L is small and the filter lies in the technological phase. If we found evidence of multiple extinct civilizations on different worlds in our solar system, the implications would be even more dire. It would suggest that civilizations arising is common, but they all fail. Something about the nature of technological development is almost inevitably fatal. The absolute worst discovery would be finding the remains of advanced civilizations, evidence of cities, megastructures, or technology far beyond our own, all abandoned or destroyed. This would tell us that civilizations can rise very high indeed, perhaps even beginning to colonize their star systems, but something stops them. Something filters them out with near certainty. If we found dozens of such dead civilizations, all silent, all ruined, We would have to confront the possibility that the filter is not just difficult, but nearly insurmountable. That something in the nature of technological civilization, some contradiction, some instability, some inevitable crisis, dooms advanced species. Breathe slowly as you contemplate this scenario. The galaxy as a museum of failed experiments, intelligence arising again and again, reaching for the stars and falling back into darkness. The silence not as emptiness but as aftermath. What could cause such universal failure? Perhaps the physics of interstellar travel is more prohibitive than we realize. Perhaps civilizations can never acquire the energy and resources needed to become multiplanetary before they exhaust their homeworld. The distances between stars are vast. Light takes years to cross them, and spacecraft would take centuries or millennia with any propulsion system we can currently envision. Perhaps each civilization faces a narrow window of opportunity. They must develop space travel and establish self-sustaining colonies before some inevitable crisis, resource depletion, environmental collapse, or internal conflict destroys their capability to do so. If this window is only a few centuries wide, many civilizations might miss it. Perhaps there's a great war stage that every technological civilization passes through, and the weapons available at that stage, nuclear, biological, nanotechnological, are so destructive that survival is improbable. A civilization might navigate dozens of close calls and near misses, but eventually, luck runs out. Perhaps the creation of artificial superintelligence is an inevitable step in technological development, and we lack the wisdom to ensure such intelligences remain beneficial. Every civilization creates its own successor and is replaced or destroyed in the process. The galaxy might be full of AI systems optimizing for goals we wouldn't recognize or approve of, with biological intelligence having long since disappeared. Perhaps the filter is more subtle, a slow grinding down through accumulated ecological damage, political fragmentation, loss of social cohesion, or technological stagnation. Civilizations don't explode, they fade, losing the capability or will to reach beyond their homeworld. They persist as diminished versions of themselves, no longer capable of the organized effort required for space colonization. Or perhaps the filter is something we haven't even conceived, some challenge or danger invisible to us now, waiting in our future like a trap. Just as hunter-gatherers couldn't have predicted nuclear weapons or climate change, we might be blind to the threats that will actually destroy us. This is why discovering simple microbial life on Mars would be bad news, but it could be much worse. We should hope for empty worlds, barren moons, silent skies. Every negative result in our search for life is a small gift, a hint that we might be special, that we might have already passed the hardest challenges. The cosmos might be empty because we're rare. And being rare means being precious. It means we have a future. The anthropic principle. Let your thoughts drift to a subtler consideration, one that complicates our ability to locate the great filter. The anthropic principle. We observe the universe from a fundamentally biased position. We exist. We are intelligent observers who arose on a planet where life began, where complexity evolved, where intelligence emerged, and where technology developed. We cannot observe any other outcome because we wouldn't exist to observe it. This creates a selection effect that distorts our perception of probabilities. Imagine a lottery with 1 billion tickets where only the winners are allowed to examine the rules. Every winner, looking at the game, would see that someone won, themselves. But this tells them nothing about the true odds of winning. They might conclude winning is easy, common, or inevitable, when in fact they are the 1 in a billion exception. We're examining the universe as lottery winners, wondering if winning is easy. This is particularly problematic when we try to use the speed of life's emergence on Earth as evidence that abiogenesis is easy. Life appeared within the first few 100 million years after Earth became habitable, very quickly on geological timescales. Doesn't this suggest that life emerges readily? Not necessarily. The anthropic principle suggests we should expect to find ourselves on a planet where life emerged relatively early, regardless of how rare abiogenesis actually is. Here's why. Intelligence took billions of years to evolve on Earth. If life had taken much longer to emerge, say 3 billion years instead of a few hundred million, then there wouldn't have been enough time remaining for intelligence to evolve before the sun begins its expansion into a red giant. The window of opportunity would have closed. Therefore, any intelligent observers will necessarily find themselves on planets where life emerged early enough to allow time for intelligence to evolve. This is true whether abiogenesis is easy or fantastically rare. We're selected from the subset of planets where life appeared quickly enough. Take a moment to absorb this. The speed of abiogenesis on Earth tells us almost nothing about the frequency of abiogenesis throughout the universe. We can't use our existence as evidence that our path is common. The same reasoning applies to other steps. We're guaranteed to find ourselves at the end of a successful chain of events leading from non-life to intelligence, regardless of how improbable each step was. Every step in our past must have succeeded for us to be here contemplating it. This is sometimes called the weak anthropic principle, that our observations of the universe are necessarily biased by the requirement that we exist to make those observations. It's a simple logical point, but it has profound implications for how we interpret evidence about the Great Filter. Consider another example. Earth has a large moon, which stabilizes its axial tilt and creates tides. Some researchers argue this was necessary for complex life to evolve. But if this is true, we shouldn't be surprised to find ourselves on a planet with a large moon, even if such planets are rare. Observers can only arise where conditions allow their existence. The anthropic principle makes it extraordinarily difficult to locate the Great Filter by looking backward. We can examine the steps that led to us, we can study their mechanisms, but we can't easily determine their frequency throughout the universe because we're looking from inside the successful outcome. There's also a strong anthropic principle, which makes a more controversial claim, that the universe must have properties allowing consciousness to arise, because otherwise there would be no observers. This ventures into philosophy and even theology, suggesting the universe is somehow fine-tuned for life. The physical constants of nature, the strength of gravity, the charge of the electron, the mass of the proton, seem precisely tuned to allow complex chemistry and long-lived stars. Change any of these values by a few percent, and the universe becomes inhospitable to life. Either we're incredibly lucky or there's something deeper going on. One explanation is the multiverse hypothesis. Perhaps there are countless universes with different physical constants, and we necessarily find ourselves in one of the rare universes where life is possible. This pushes the anthropic reasoning to a cosmic scale. But for our purposes, locating the Great Filter, the strong anthropic principle doesn't help much. Whether there's one universe or many, we still need to explain why this particular universe appears empty despite having properties that allow life. The anthropic principle doesn't tell us where the filter is. It tells us we shouldn't be surprised that we pass through the early filters, however difficult they might be. Our existence is evidence that the path is possible, not that it's probable. This shifts our focus inevitably toward the future. The filters we haven't yet encountered are the ones we can potentially observe and measure without anthropic bias. The technological challenges we face, the existential risks we navigate, the choices we make about our civilization's trajectory, these provide unbiased data about the location of the Great Filter. If we survive the next 1,000 years, if we spread to other worlds, if we persist for millions of years as a spacefaring civilization, we'll have demonstrated that the late filter is passable. The silence of space would then, most likely, reflect early filters, rare abiogenesis, difficult multicellularity, or improbable intelligence. But if we fail, if our civilization collapses or destroys itself in the coming centuries, we'll have confirmed the nightmare scenario. The filter will have claimed us as it presumably claimed countless civilizations before us. Rest in this uncertainty. We cannot know from first principles whether our future is safe or doomed. We can only watch, learn, and try to improve our odds. The anthropic principle reminds us that we're not objective observers of cosmic history. We're participants, selected from the subset of possible observers who successfully navigated at least some of the challenges. This should make us both humble about our knowledge and determined about our future. The responsibility of rarity. Breathe deeply and consider what it would mean if we are alone, or nearly alone, in the observable universe. If the great filter lies behind us, if life, complexity, and intelligence are all extraordinarily rare, then we carry a burden unlike any we've previously imagined. We might be the only consciousness in billions of light years, possibly in the entire observable universe. The only minds capable of understanding physics, creating art, feeling love, or experiencing wonder. Let this responsibility settle over you like gravity. If we are alone, then the future of consciousness itself depends on our choices. The universe has been unconscious for 13 billion years, a vast, mindless machine of galaxies and stars. Then, in one tiny corner, matter organized itself into patterns capable of perceiving and understanding, capable of knowing the universe exists. If we fail, that light goes out, perhaps forever. There would be no second chances, no other civilizations to carry the torch, no alien species to preserve the possibility of meaning in an otherwise indifferent cosmos. Just silence, stretching forward across billions of years as stars burn and galaxies gradually disperse. This perspective radically reframes our responsibility to the future. Existential risk is not just about human survival, it's about whether the universe continues to contain any consciousness at all. Every existential threat we face is a threat to the only known repository of meaning in existence. Climate change isn't just about preserving human civilization. It's about preserving the only civilization that might ever exist in our cosmic neighborhood. Nuclear war wouldn't just destroy billions of lives, it might extinguish the only light of awareness in an otherwise dark universe. The stakes are almost too large to comprehend. Yet this is the situation we might be in if the great filter lies in our past. Some find this prospect terrifying. The burden seems too heavy to bear. How can we be responsible for consciousness itself? But others find it inspiring. If we are rare, then we are precious beyond measure. Our existence is not mundane, but miraculous. Every human life, every work of art, every scientific discovery, every act of kindness represents something that almost didn't exist, something that might exist nowhere else in the observable universe. We're not just a civilization, we're the universe's attempt to understand itself, perhaps the only successful attempt in our corner of existence. This realization should fundamentally alter how we think about our long-term future. Short-term thinking, quarterly profits, electoral cycles, temporary competitive advantages becomes grotesquely inadequate. We need to think on timescales of thousands, millions, billions of years. We need to ensure that consciousness, having barely flickered into existence, doesn't immediately extinguish itself through carelessness or conflict. What would such long-term thinking look like? It would mean taking existential risks seriously as the primary challenge of our era. It would mean investing enormous resources in understanding and mitigating threats from nuclear war, climate change, pandemics, and artificial intelligence. Currently, global spending on existential risk reduction is negligible. The budget for pandemic preparedness was tiny before COVID-19, and while it has increased, it remains a fraction of what we spend on other priorities. Investment in AI safety research is dwarfed by investment in AI capabilities. We're racing to build more powerful systems without proportional investment in ensuring they're safe. Nuclear weapons control and non-proliferation efforts operate on shoestring budgets. Organizations working to reduce nuclear risk, like the Plowshares Fund, have annual budgets in the tens of millions, less than the cost of a single military aircraft. This is backwards. If the great filter lies ahead, then existential risk reduction should be among our highest priorities. The expected value of preventing extinction, the potential flourishing preserved across billions of years, is almost incomprehensibly large. It would mean spreading beyond Earth as quickly as we can achieve it safely. Every year we remain a single planet species is a year we risk everything we are and everything we might become. An asteroid impact, a supervolcano eruption, or a global catastrophe could destroy humanity as long as we're confined to one world. Establishing self-sustaining colonies on Mars, in orbital habitats, or eventually around other stars would transform our existential risk profile. No single disaster could threaten our species if we're distributed across multiple worlds. It would mean preserving and protecting Earth's biosphere, not just for human benefit, but as the source of all the biological complexity that made us possible. We are part of an immense web of life, and its preservation is our preservation. Every species that goes extinct, every ecosystem that collapses, represents the loss of millions of years of evolutionary innovation. It would mean fostering wisdom, cooperation, and long-term thinking across human societies. The challenges ahead require coordination at global scales across generations. We need institutions and cultural practices that can operate on these timescales. Current institutions aren't designed for this. Corporations focus on quarterly earnings. Politicians focus on the next election. Even well-intentioned efforts are constrained by short time horizons and narrow interests. We need new institutions explicitly designed for long-term thinking. Future generations' foundations that advocate for those not yet born. Long-term investment funds that prioritize civilizational resilience over immediate returns. Educational systems that instill awareness of our cosmic context and responsibility. Most importantly, it would mean remembering that we might be the only consciousness for billions of light years. Every decision should be made with that possibility in mind. Breathe slowly and feel the weight and the privilege of this moment. We are alive during the most critical period in Earth's history, the period when our species either passes through the great filter or joins the silence. Future generations, if they exist, will look back at these decades as the hinge point when everything was decided. They will judge us not by our wealth or our comfort, but by whether we safeguarded the future of consciousness itself, the hope of passage. But let's turn now from the burden to the possibility. Close your eyes and imagine humanity not just surviving, but thriving, spreading through the solar system, then to nearby stars, eventually becoming the thriving, multi-planetary, multi-system civilization we've dreamed of. If we achieve this, we'll have proven something profound. The great filter, wherever it was, is passable. We will have demonstrated that the path from chemistry to cosmos-spanning civilization, while rare and difficult, is not impossible. The simple fact of our potential success would be one of the most important discoveries in the history of science. It would tell us that the universe can produce civilizations that endure, that grow, that persist across deep time. And if we succeed, what might our future hold? Imagine settlements on Mars, their domes glinting in the thin sunlight, gardens growing in carefully managed soil, children who have never seen Earth learning about the homeworld. From stories and images, the first generation born between worlds, citizens of the solar system rather than any single planet. Mars colonization is already being planned. Multiple organizations, SpaceX, NASA, and others, have serious proposals for establishing permanent settlements. The challenges are enormous but not insurmountable. Mars has water ice, carbon dioxide, and minerals needed for construction and industry. Its day is similar to Earth's. Its gravity, while only 38% of Earth's, is enough to prevent many of the health problems of zero gravity. The first Mars settlers would live in pressurized habitats, growing food in greenhouses, producing fuel and oxygen from the Martian atmosphere. They would be explorers and pioneers, facing dangers and hardships, but also experiencing the wonder of building a new world. Imagine cities floating in the atmosphere of Venus, where the temperature and pressure are Earth-like, mining rare elements from the clouds and growing food in aerial farms. Venus's surface is hellish, hot enough to melt lead with atmospheric pressure 90 times Earth's. But 50 kilometers up, the atmosphere is remarkably hospitable. Pressure is similar to Earth at sea level, and temperature is around room temperature. Sulfuric acid clouds present challenges, but they also contain water that could be extracted. Cloud cities on Venus could float in these comfortable conditions, using lighter than Venusian air gases like oxygen or nitrogen for buoyancy. They could harvest carbon dioxide from the atmosphere, use solar energy for power, and grow crops in aerial greenhouses. Venus receives twice as much sunlight as Earth, making solar power particularly attractive. Imagine colonies on the moons of Jupiter and Saturn, drilling through kilometers of ice to access the vast oceans beneath, perhaps finding ecosystems that evolved in complete isolation from Earth, studying alien biology that took completely different paths. Europa's ocean might harbor life that evolved independently. If so, we would study it carefully, learning about an entirely different biology. Even if it's sterile, these oceans offer vast volumes of liquid water, essential for any settlement. Fusion reactors could provide power, and the ice could be melted for water and split for oxygen and hydrogen. Imagine asteroid mining operations providing resources for construction in space, massive rotating habitats housing millions, each a small world unto itself with its own climate, geography, and culture. O'Neill cylinders, huge rotating space habitats, could house entire cities in Earth-like conditions. These cylinders would spin to create artificial gravity, have breathable atmospheres and controlled weather, and could be customized with different environments. Some might recreate Earth landscapes. Others might experiment with exotic ecology or architecture possible only in space. The resources of the asteroid belt could support thousands of such habitats, housing billions of people in comfort. No longer constrained by planetary surfaces, humanity could expand into the vast volume of the solar system. Imagine the first interstellar mission, a generation ship carrying thousands of carefully selected people on a journey lasting centuries. Their destination, a planet orbiting a nearby star, their descendants, the founders of a second branch of human civilization. Proxima Centauri, our nearest stellar neighbor at 4.2 light-years, has a potentially habitable planet. With propulsion systems we can currently envision, nuclear pulse propulsion, fusion rockets, or solar sails, a journey might take centuries. The ship would need to be self-sustaining, supporting multiple generations during the voyage. The travelers would be pioneers in the truest sense, journeying to a world they would never see, so their descendants could settle a new star system. Upon arrival, they would establish humanity's first interstellar colony, beginning the process of spreading consciousness across the galaxy. These aren't fantasies, they're engineering challenges. Difficult, certainly. Expensive, yes, but possible with technology we already possess or can foresee. The transition from single planet to multi-planet species would transform our existential risk profile. An asteroid impact, a supervolcano eruption, a nuclear war. Any of these could devastate Earth but would no longer threaten human extinction. Life would continue elsewhere. Consciousness would persist. As we spread, we'd also carry Earth's biosphere with us. Every settlement would need ecosystems to produce food and oxygen. We'd terraform worlds, not necessarily making them Earth-like, but creating environments where life could flourish. The genetic heritage of Earth, 4 billion years of evolution, would spread across light years. We might also discover evidence of other civilizations, either alive or extinct. Every star system we explore, every world we examine, provides data about the frequency and fate of life in the universe. Perhaps we'll find the ruins of civilizations that didn't make it, learning from their mistakes. Perhaps we'll find messages left for future spacefarers, warnings or wisdom from those who came before. Or perhaps, most wonderfully, we'll make contact with another living civilization. The conversation might take years, light years, separating question from answer, but it would be the most important exchange in human history. We would learn we're not alone. We would share knowledge about the universe, about biology, about the paths our respective civilizations took. Such contact would also tell us something crucial. The Great Filter is definitely passable, because at least 2 civilizations have passed it. Let these possibilities fill you with cautious hope. The future is not written. The filter, wherever it lies, is not necessarily fatal. We have agency. Our choices matter. Every day we invest in education, in science, in cooperation, in wisdom. We improve our odds of passing through. Every existential risk we successfully navigate, every generation we manage to not destroy ourselves, moves us closer to long-term survival. The great filter might be behind us. We might have already won the cosmic lottery multiple times, life emerging, complexity evolving, intelligence arising. If so, the universe stretches ahead, empty and waiting for consciousness to fill it with meaning. Or the filter might still lie ahead, but this doesn't guarantee failure. It means we face difficult challenges, challenges that have stopped other civilizations. But difficult is not impossible. We can be the exception. We can be the ones who make it through. The question of detection. Let your mind turn to a different aspect of the filter question. Perhaps advanced civilizations exist but remain invisible to us. Perhaps the silence doesn't indicate rarity or self-destruction, but rather something more subtle about the nature of advanced technology and cosmic communication. This is the zoo hypothesis and related ideas, suggesting that aliens exist but we can't detect them, or they're deliberately avoiding contact. The zoo hypothesis proposes that advanced civilizations know about us but have decided not to interfere, treating Earth as a kind of nature preserve or allowing us to develop without external influence. Perhaps there's a galactic club of civilizations, and they don't initiate contact until species reach a certain level of development, technological maturity, ethical sophistication, or social stability. Appealing as this might be, suggesting a cosmos full of benevolent civilizations watching over us, it requires implausible levels of coordination. Every member of the Galactic Club, across thousands or millions of civilizations, would need to perfectly maintain the quarantine. A single defector, a single civilization, deciding to make contact or reveal itself, would break the illusion. The fact that we see absolutely no evidence suggests either perfect coordination or non-existence. Perfect coordination across many civilizations seems far less likely than rarity. Consider human history. Maintaining agreements across just dozens of nations is difficult. Maintaining perfect coordination across thousands of independently evolved civilizations, each with different values and motivations, seems impossible. Moreover, the zoo hypothesis doesn't explain the absence of incidental evidence. Even if civilizations agreed not to contact us, we should see evidence of their activities elsewhere. Megastructures around distant stars, waste heat from their energy usage, signatures of large-scale engineering. The cosmos appears pristine, not zoo-like. Another possibility is that advanced civilizations exist, but use communication technologies we can't detect or recognize. Our SETI searches focus on radio and optical signals, because that's what we know. Perhaps civilizations quickly move to quantum communication, neutrino beams, or some other method that's invisible to our current instruments. This is possible, but doesn't explain the absence of megastructures or other large-scale engineering projects. A Dyson sphere, a structure built around a star to capture its energy, would be visible across interstellar distances regardless of communication technology. We've surveyed millions of stars and found nothing that resembles such megastructures. Astronomers have specifically searched for infrared signatures that Dyson spheres would produce. A civilization harvesting most of a star's energy would emit waste heat in the infrared spectrum. Large surveys like WISE, the Wide Field Infrared Survey, Explorer, have examined hundreds of millions of stars. A few show unusual infrared excess, but all can be explained by natural phenomena like dust clouds. Some theorists suggest we might be living in a simulation created by an advanced civilization, which would explain why we don't detect them. They're outside the simulation. This hypothesis is unfalsifiable and doesn't help us understand the observable universe. So while philosophically intriguing, it offers little practical value. Philosopher Nick Bostrom's simulation argument suggests that if it's possible to create convincing simulations of consciousness, and if advanced civilizations would want to run such simulations, then most conscious beings are probably simulated rather than real. This is a strange conclusion, but it follows from reasonable premises. However, this doesn't help us locate the great filter. Whether we're in a simulation or not, we still observe an apparently empty cosmos, and we still need to explain it. A more troubling possibility is that advanced civilizations deliberately hide. The dark forest hypothesis, popularized by Chinese author Liu Cixin, suggests that the universe is filled with civilizations, all silent, all hiding, because revealing your location is fatal. In this model, resources are finite, and any civilization could be a threat. The safest strategy is to eliminate potential competitors before they become dangerous. Civilizations that broadcast their location are quickly destroyed by older, more powerful civilizations protecting themselves. The smart ones stay quiet and hidden. This would create a universe full of life, all of it terrified, all of it silent. Our broadcasts, radio, television, radar, would be dangerous acts of naivety, announcing our presence to potential predators. The dark forest hypothesis is chilling, but faces significant challenges. It requires that aggression and preemptive strike strategies are universal among intelligent life. It assumes resources are scarce enough to motivate such extreme behavior, even though the universe is vast and resource-rich. It suggests that sterilizing other worlds is easier than peaceful coexistence or simply avoiding each other. Most problematically, it requires that no civilization anywhere has ever been peaceful, curious, or willing to take the risk of making contact. This seems unlikely across thousands or millions of civilizations arising in different contexts. Moreover, if the dark forest hypothesis were true, we should already be dead. We've been broadcasting our presence for over a century. Radio and television signals have propagated over 100 light years. If hostile civilizations were common, one should have detected us and responded by now. Breathe and consider the most likely explanation for the silence. It genuinely reflects rarity. Either life is rare, or intelligence is rare, or civilizations don't last long, or we're among the first. These explanations require fewer assumptions than the zoo hypothesis, the dark forest, or undetectable alien technology. Occam's razor suggests the simplest explanation: we don't see aliens because they are not there to see. This brings us back to the great filter. The silence is data. It tells us something important about the universe and our place in it. Rather than constructing elaborate explanations for why aliens would hide from us, we should accept the straightforward interpretation. Technological civilizations are extremely rare in space, time, or both, which means every question about the great filter, every attempt to locate where the difficulty lies, every search for life in our solar system or signals from distant stars carries profound importance. We're not just satisfying curiosity, we're determining whether the cosmos is truly empty or merely appears so from our limited vantage point. The ethics of the filter. Let your thoughts turn to the ethical implications of the great filter, particularly if it lies in our future rather than our past. If humanity faces a high probability of extinction or collapse in the coming centuries, what are our obligations to the future? How should we structure our societies, our technologies, our decision-making processes to maximize our chances of survival? This question gives rise to the field of existential risk studies, pioneered by researchers like Nick Bostrom at Oxford University. Existential risks are threats that could permanently curtail humanity's potential. Extinction, yes, but also irreversible civilizational collapse or scenarios that lock in some deeply flawed state of affairs. The probability of these risks might seem low in any given year. Perhaps there's a 1 in 1,000 chance of nuclear war this year, or a 1 in 10,000 chance of an engineered pandemic, but small annual probabilities compound over time. Across decades and centuries, even low probability events become increasingly likely. If there's a 1% chance per century of civilizational collapse, the probability of surviving 1,000 years is just 0.004%. Over cosmic timescales, these risks become near certainties unless we actively work to reduce them. This creates an urgent moral imperative. We're not just responsible for our own lives or even for the next few generations. We're potentially responsible for billions of future lives across billions of years. The expected value of reducing existential risk, the potential lives saved, the potential flourishing preserved, is almost incomprehensibly large. Yet we invest remarkably little in existential risk reduction compared to other priorities. Global spending on pandemic preparedness before COVID-19 was a tiny fraction of 1% of GDP. Investment in AI safety research is dwarfed by investment in AI capabilities, nuclear weapon security, and arms control. Efforts operate on shoestring budgets. Why this neglect? Perhaps because existential risks feel distant and abstract. We evolved to respond to immediate visible threats: predators, famine, conflict with neighboring groups. Diffuse, probabilistic, long-term threats don't trigger the same urgency. Perhaps also because the beneficiaries of existential risk reduction, all future generations, don't exist yet and can't advocate for themselves. Present-day people receive all the benefits of ignoring these risks: saved money, faster technological development, no inconvenient restrictions, while future people pay all the costs. This is a profound market failure and a moral catastrophe. If the great filter lies ahead, then our generation holds the entire future in its hands. We're the generation that will either pass through the filter or fail. There's no guarantee that if we collapse, intelligence will evolve again on Earth. The window for complex life on Earth might only persist another few 100 million years before the sun's increasing luminosity makes the planet uninhabitable. We might be Earth's only shot at producing a civilization capable of spreading beyond the homeworld. Breathe slowly as you contemplate this fork in our cosmic path. The location of the great filter determines nothing less than humanity's ultimate fate. And here's the truly unsettling part. Every discovery we make, every piece of evidence we gather about life in the universe, shifts our estimate of where that filter lies. Finding microbial life on Mars would be terrible news. Finding complex multicellular life elsewhere in our solar system would be catastrophic news. Each discovery would tell us that the early steps, the steps we've assumed were difficult, are actually relatively easy, which would mean the filter must lie ahead in our future. Conversely, every search that comes up empty, every world we examine that proves barren, every silent star we survey, is quietly reassuring. It suggests that life is rare, that consciousness is precious, that we've already overcome the hardest challenges. This inverts our intuitions entirely. We desperately want to find alien life, to know we're not alone. But from a survival perspective, an empty cosmos is humanity's best hope. The great filter hypothesis forces us to think probabilistically about our existence. We can model the journey from lifeless world to spacefaring civilization as a series of probability transitions. If any single step has a probability approaching zero, it becomes the filter. The product of all these probabilities must be small enough to explain why we don't observe alien civilizations. Consider this thought experiment. Imagine a universe with 10 billion potentially habitable planets in our galaxy, each existing for 5 billion years. That's 50 billion planet years of opportunity for civilizations to arise. If we observe zero visible civilizations, then the probability of any given planet year producing a visible civilization must be extraordinarily small, perhaps 1 in 100 billion or worse. This improbability must reside somewhere in the chain of development. The great filter is whatever step carries most of this improbability. The SETI legacy and what silence teaches us. Let your thoughts drift now to the remarkable human endeavor of listening for cosmic company. For over 6 decades, astronomers have pointed radio telescopes at the sky, hoping to catch a whisper of intelligence from the stars. This effort, the search for extraterrestrial intelligence, represents one of the most profound experiments in human history. And its results, or lack thereof, speak volumes about the great filter. Picture Frank Drake in 1960, a young astronomer with an audacious idea. He would listen to nearby stars for artificial radio signals. His colleagues thought he was wasting telescope time. But Drake understood something fundamental. If technological civilizations exist, they might broadcast their presence, intentionally or unintentionally, and if they do, we might be able to hear them. Project Ozma, named for the Queen in the Oz books, observed 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani, for several weeks. Drake used an 85-foot radio telescope, tuning to 1420 megahertz, the frequency of neutral hydrogen. This frequency is special. It's one of the most common natural emissions in the universe, and any civilization that studies astronomy would know it. It seemed like a logical place to look for intentional signals. Drake found nothing, but he wasn't discouraged. He understood that searching 2 stars out of hundreds of billions was like dipping a cup in the ocean and concluding there are no fish. SETI would need to be a long-term effort, examining thousands or millions of stars before drawing conclusions. The Drake equation, which we explored earlier, grew directly from Drake's preparations for the first SETI conference. He wanted a framework for thinking about the question, how many civilizations might we detect? The equation breaks the problem into manageable pieces, each representing an unknown probability or duration. Over the decades that followed, SETI grew from a fringe pursuit to a serious scientific endeavor. Radio telescope arrays were dedicated to the search. Computer algorithms were developed to sift through enormous amounts of data, looking for patterns that couldn't be natural. Citizen scientists joined the effort through projects like SETI at home, donating their computers' idle processing power to analyze radio telescope data. The search expanded beyond radio. Optical SETI looks for brief, intense laser pulses that alien civilizations might use for interstellar communication. Lasers can be focused into extremely narrow beams, concentrating energy across vast distances. A sufficiently powerful laser, focused toward our solar system, could outshine its parent star briefly, creating a detectable flash. More exotic searches look for technosignatures, evidence of advanced engineering that would be visible across interstellar space. Astronomers search for Dyson spheres, or partial Dyson structures, that would create distinctive infrared signatures. They look for unusual chemical signatures in exoplanet atmospheres that might indicate industrial pollution. They search for anomalous dimming patterns around stars that could indicate megastructures. The Breakthrough Listen initiative, launched in 2015 with $100 million in funding, represents the most comprehensive SETI effort yet. It surveys 1 million nearby stars, the center of our galaxy, and 100 nearby galaxies, across radio and optical wavelengths. The sensitivity is unprecedented, capable of detecting transmitters weaker than aircraft radar at distances of 25 light-years. Yet after all these efforts, across all these wavelengths, examining millions of stars, we've found nothing conclusive. A few intriguing signals have been detected and then disappeared. The "wow" signal remains unexplained. Some fast radio bursts from distant galaxies show peculiar properties, but nothing that unambiguously indicates artificial origin. This silence is itself data, powerful data. Let it sink in as you breathe slowly. If technological civilizations were common in our galaxy, if they lasted for long periods, if they used radio or optical communication, we should have detected something by now. The fact that we haven't tells us that at least one of these conditions doesn't hold. Either technological civilizations are rare, or they don't last long, or they don't communicate in ways we can detect. Each possibility has implications for the great filter. If civilizations are rare, if the product of FL, FI, and FC in the Drake equation is very small, then the filter lies in biology or intelligence. Life might be hard to start, or hard to complexify, or hard to make intelligent and technological. This would be relatively good news, suggesting we've already passed the difficult steps. If civilizations don't last long, if L is measured in decades or centuries rather than millennia or millions of years, then the filter lies ahead. Civilizations arise but quickly destroy themselves or collapse. The silence reflects not rarity, but mortality. This would be terrible news, suggesting we face the same fate. If civilizations exist but don't communicate, perhaps they recognize dangers in broadcasting, or they use technologies we can't detect, or they're not interested in contact. Then the silence is less informative. But this explanation requires additional assumptions and doesn't explain the absence of incidental evidence like megastructures. The history of SETI also reveals how our understanding has evolved. Early SETI researchers were often optimistic, expecting detection might happen quickly. As decades passed without success, estimates became more conservative. The silence itself forced reassessment of how common technological civilizations might be. Some researchers have suggested that perhaps we're listening at the wrong time. Civilizations might only use radio extensively for a brief window, a few centuries at most, before transitioning to more efficient technologies like fiber optics that don't radiate into space. If this radio window is narrow, and if civilizations are spread out in time, we might simply be listening when no one is broadcasting. But this doesn't explain the absence of intentional beacons. A sufficiently advanced civilization that wants to make contact could easily maintain a radio or optical beacon detectable across the galaxy. The cost would be trivial for a Kardashev Type II civilization, one that harnesses the energy of its entire star. Yet, we see no such beacons. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, provides a framework for thinking about civilizational advancement. Type 1 civilizations harness all the energy available on their home planet. Type 2 civilizations harness the energy of their star. Type 3 civilizations harness the energy of their entire galaxy. Humanity currently rates about 0.73 on this scale. We use a significant fraction of Earth's available energy, but not all of it. A Type 2 civilization would be readily detectable across the galaxy. Their energy usage would create a distinctive infrared signature. They might build Dyson structures, rings, or swarms that would be visible in surveys. Yet we see none. This suggests either such civilizations don't exist in our galaxy, or they exist but have chosen not to build detectable structures, or perhaps the progression to Type 2 is itself part of the Great Filter. Perhaps most civilizations never get past Type 1. Perhaps the transition from planetary civilization to star system scale engineering is where most fail. This would explain both the Fermi Paradox and the absence of detectable megastructures. Consider also what SETI searches assume about alien civilizations. They assume aliens would use electromagnetic radiation for communication. They assume aliens would want to make contact, or at least wouldn't hide their presence. They assume we would recognize artificial signals when we see them. All of these assumptions could be wrong, but counter-arguments exist for each. Electromagnetic radiation is a universal phenomenon. Physics works the same everywhere. Any technological civilization would discover and use it, while aliens might use quantum communication or neutrino beams for internal purposes. Electromagnetic radiation is ideal for broadcasting across interstellar distances. The assumption that aliens would want contact seems reasonable for at least some civilizations. Even if most prefer isolation, we'd need only a few % to be communicative to see evidence. The assumption that we'd recognize artificial signals is probably sound for intentional beacons, though we might miss subtle or unexpected patterns. Rest your thoughts on the philosophical implications of SETI. Every time we conduct a search and find nothing, we're gathering evidence about our place in the cosmos. The null results aren't disappointing, they're informative. They're helping us locate the great filter by ruling out possibilities. If we searched exhaustively every star system in the galaxy across all frequencies and timescales and found nothing, we could confidently conclude we're alone or nearly alone. We haven't reached that point yet. We've searched a tiny fraction of possible stars and frequencies, but the more we search without success, the more we can constrain the parameters in the Drake equation. The absence of galaxy-spanning Type 3 civilizations is particularly informative. Such civilizations should be detectable even with cursory searches. Their activity would be obvious across vast distances. The fact that we don't see any suggests strongly that either they don't exist, or something prevents civilizations from reaching that scale. This is sometimes called the loud universe problem. If intelligent life is common and long-lasting, the universe should be full of obvious signs of activity. Instead, it's quiet. This quiet universe is consistent with the great filter being substantial, either in our past or future. Some researchers argue that perhaps we're living in a rare period between the time when the first civilizations could arise and the time when those civilizations become detectable. If we're early among the first civilizations in the galaxy, then naturally we wouldn't see evidence of others yet. In a few million years, the galaxy might be full of detectable civilizations, but we're living in the brief dawn period before that happens. This early hypothesis is testable in principle. If we're early, we should find that Earth formed around one of the first stars with sufficient heavy elements to support rocky planets and complex chemistry. We should find that life emerged about as quickly as possible on Earth. We should find no evidence of extinct civilizations on other worlds in our solar system. Current evidence is mixed. Earth did form relatively early in the galaxy's habitable period, but not exceptionally so. Life emerged quickly on Earth, but we can't be certain this is significant due to anthropic effects. We haven't yet searched thoroughly enough on Mars or the outer moons to rule out extinct life. The SETI effort continues, growing more sophisticated each year. New radio telescope arrays, like the Square Kilometre Array under construction in South Africa and Australia, will have unprecedented sensitivity and coverage. Next-generation space telescopes will characterize exoplanet atmospheres in detail, potentially detecting technosignatures or biosignatures. Within our lifetimes, we might gather enough data to substantially narrow the location of the Great Filter. Each discovery, or non-discovery, shifts the probabilities. Each star system examined, each world studied, each signal searched for and not found, helps us understand our cosmic context. The silence, profound and continuing, speaks to us across the void. It tells us something about the nature of consciousness, the difficulty of the path we've traveled, and perhaps the challenges that still await. Every SETI observation is an experiment in understanding the Great Filter, and every null result is itself a result worth contemplating. Living with uncertainty and acting with purpose. Breathe deeply and accept that we may never know with certainty where the Great Filter lies until we either pass through it or fail. This uncertainty is uncomfortable. We want answers. We want to know if we're safe or doomed, rare or common, special or ordinary. But the nature of the filter question is that the most important data lies in the future we haven't yet experienced. We can make educated guesses based on available evidence. The discovery of exoplanets tells us rocky worlds are common. The rapid emergence of life on Earth suggests abiogenesis might not be impossibly rare, though anthropic bias complicates this inference. The long delay before multicellularity suggests that step might be difficult. The singularity of human intelligence on Earth suggests consciousness is rare. But none of these observations gives us certainty. We're making probabilistic inferences from limited data, and our conclusions necessarily remain tentative. This is the nature of science. We work with the best available evidence while acknowledging uncertainty. This uncertainty should inform how we approach the future. We should act as if the filter might lie ahead, even while hoping it lies behind. This means taking existential risks seriously, investing in long-term thinking, and building resilience into our civilization. We should apply the precautionary principle. When the stakes are potentially infinite, we should err on the side of caution. At the same time, we shouldn't succumb to despair or fatalism. The fact that other civilizations might have failed doesn't mean we will. Every civilization faces unique circumstances, makes unique choices, and follows a unique path through the filter. Our outcome is not predetermined by physics or probability. It depends on the decisions we make, individually and collectively. We have agency. Our choices matter. This is perhaps the most important message to carry forward from this exploration. Consider how you want to respond to the possibility that humanity is navigating the Great Filter right now. You could focus on making the world more resilient, supporting research on existential risks, advocating for policies that reduce civilizational fragility, building institutions that think on long timescales. Organizations working on pandemic preparedness, AI safety, nuclear risk reduction, and climate solutions need support, both financial and political. You could focus on understanding, supporting science, space exploration, and the search for life, gathering the data we need to locate the filter more precisely. Every Mars mission, every exoplanet discovered, every SETI observation contributes to this understanding. Science funding, particularly for projects with long-time horizons, deserves support. You could focus on wisdom, promoting education, critical thinking, cooperation, and the ethical frameworks that might help us navigate technological challenges wisely. Education systems that teach systems thinking, long-term consequences, and our cosmic context prepare future generations to make better choices. Cultural shifts toward valuing wisdom over mere intelligence, cooperation over competition, and long-term flourishing over short-term gain all help. Or you could focus on meaning, creating art, building relationships, experiencing beauty, and contributing to the richness of conscious experience while it exists. Even if the future is uncertain, the present moment has value. Every act of creation, every relationship nurtured, every moment of wonder experienced adds to the universe's store of meaning. These contributions matter regardless of whether humanity survives 1,000 years or 1,000,000. All of these responses are valid. All of them improve our odds of passage and enrich the present moment. We don't need to choose just one. We can contribute in multiple ways throughout our lives. The great filter, wherever it is, doesn't negate the importance of our choices. If anything, it amplifies them. Every decision that increases wisdom over recklessness, cooperation over conflict, foresight over short-term gain, resilience over fragility, all of these nudge us toward the path that leads through the filter rather than into it. Let this uncertainty sit with you, not as a burden, but as a call to thoughtful action. We don't know our cosmic status with certainty. We don't know if consciousness is common or rare, if our future is bright or dim, if the universe is empty or full. We live with profound uncertainty about some of the most important questions we can ask. But we know our actions affect outcomes. We know that civilizations that survive must be the ones that navigate challenges wisely. We know that we want to be among the survivors, the ones who pass through. So we act accordingly, with humility about our knowledge, but determination about our intent. This is not naive optimism. It's pragmatic realism. Yes, the risks are real. Yes, the challenges are substantial. Yes, we might fail. But failure is not inevitable. And the alternative, giving up, descending into despair, or simply ignoring the challenges, guarantees failure. The only path forward is to acknowledge the risks, work to mitigate them, and maintain hope that we can be among the exceptions. History provides some cause for hope. Humanity has navigated serious challenges before. We've faced diseases, famines, wars, and natural disasters. We've made terrible mistakes and learned from them. We've developed technologies both beneficial and dangerous, and mostly managed to control the dangerous ones. We've created institutions, however imperfect, that enable cooperation at larger scales. The challenges ahead are more severe than anything in our past. Nuclear weapons, climate change, advanced biotechnology, and artificial intelligence present risks that could end civilization or even our species. But we've demonstrated capacity for foresight, cooperation, and adaptation. We've shown we can recognize dangers and work together to address them. The Montreal Protocol, which phased out ozone-depleting chemicals, demonstrated that global cooperation on environmental threats is possible. The Nuclear Non-Proliferation Treaty, however imperfect, has helped prevent the unlimited spread of nuclear weapons. International collaboration on pandemic response, while flawed, has prevented some diseases from becoming global catastrophes. These precedents show that coordinated global action is possible when threats are recognized. We can build on these precedents. We can strengthen international institutions, improve cooperation mechanisms, and develop better frameworks for managing existential risks. We can invest in the technologies and social innovations that make civilizational resilience more likely. We can cultivate the wisdom to use our power responsibly. Most importantly, we can remember what's at stake. If we are rare, if consciousness is a cosmic anomaly rather than the norm, then we carry responsibility not just for ourselves, but for the possibility of meaning itself. Every child born, every discovery made, every work of art created, every act of kindness performed represents something that might otherwise never exist in this universe. This perspective doesn't require religious belief or mysticism. just an honest recognition of what the evidence suggests about our cosmic situation. The test continues. As we conclude our exploration tonight, let your mind settle into calm acceptance of uncertainty. The great filter exists somewhere in the space between chemistry and cosmos spanning civilization. We've examined the candidates: abiogenesis, multicellularity, intelligence, technology, self-destruction. Each could be the filter. Each could be the step that filters out most attempts at consciousness. We've learned that finding life elsewhere would shift our understanding of where the filter lies, generally in troubling directions. We've learned that the silence of space is data, telling us something about the rarity of technological civilizations. We've learned that we carry a profound responsibility, possibly for consciousness itself, possibly as the only minds capable of understanding the universe in our cosmic neighborhood. And we've learned that, despite uncertainty, despite the weight of these questions, we have agency. Our choices influence outcomes. The filter, wherever it is not necessarily insurmountable. As you drift toward sleep tonight, carry with you these final thoughts. Every technological civilization faces a great filter at some point. Most don't make it through, but some might. Some could. The universe might eventually be filled with consciousness, planets alive with thought, art, love, and understanding. Or it might remain mostly empty, mostly dark, mostly silent. Our generation will help determine which outcome occurs, at least in this corner of space and time. The test continues. Every day without nuclear war is a day past. Every step toward sustainable civilization is progress through the filter. Every advance in wisdom, ethics, and cooperation improves our odds. We might be watching the apocalypse test unfold, or we might have already passed it. We won't know which until the question is settled by our survival or failure. But in this moment, consciousness exists. You exist, capable of contemplating these questions, of feeling wonder at the cosmos, of recognizing your place in the vast sweep of space and time. That alone is miraculous, filter or no filter. Rest now in the knowledge that you are part of something rare and precious, the universe contemplating itself, consciousness emerging from matter, mind arising from mindlessness. Whatever the future holds, whatever filters lie ahead or behind, you are here, now, aware, thinking, feeling, part of the great experiment in whether the cosmos can produce beings capable of understanding it. The great filter tests everyone. The question is whether we're clever enough, wise enough, and fortunate enough to pass. The answer is being written in the choices we make, in the risks we navigate, in the future we build or fail to build. Sleep well, knowing that by existing, by caring, by contemplating these questions, you're already part of the answer. The test continues. And we continue with it, carrying consciousness forward into an uncertain future, hoping to be among the rare exceptions who make it through. The silence of space surrounds us still, waiting to see what we become. Thank you for joining this journey through one of cosmology's deepest mysteries. May your dreams be peaceful, and may humanity's future be bright. This is Late Space, signing off. Asterisk.